All right, we are now recording. Um, let's talk a couple of announcements first. I think you've heard them because you were here for the other classes, but let me get them recorded for anyone who wasn't here. And here comes Jesus. I think he was here to hear them too, but we'll go on and do it. So Jesus is here. All right. And no, maybe Jesus wasn't here to hear them, so let me make sure I make this announcement so you can hear it. In my first class, all 4 people were there. It was a small class, so they all got to hear it at once. This one you may hear it several times if people keep coming in one at a time. But here's the situation. It seems to me, and this is just a perception, that enrollment must be really down for the spring term. And because of that, the administration, I think, is beginning to panic a little bit, and maybe rightly so. And they are, someone came up with this idea. I first heard about it last Tuesday morning, and here's Esther, so good she's here to hear it. All right, so now we've got 3 people here. Top part of the alphabet is looking really strong. The bottom part has 1 person in it, and the middle part is completely vacant. So hopefully the others will be coming in. I was making this announcement. I was saying that first I heard of it was last, well, I know they've been putting out announcements earlier, but this thing that I'm about to announce now, the first I heard about it was Tuesday morning. Of course, we met Monday morning or Monday afternoon, and so I hadn't heard about this Monday afternoon. Then Wednesday, of course, was Veterans Day, so there was no school. We didn't have any class, so I couldn't post anything about it then. But here's the deal. Enrollment seems to be down for spring, so what they've decided to do is have a big push this week, Monday through Thursday, 9 in the morning until 7 in the evening, all 4 days. They're going to have advisors and we might say counselors, different people helping with advising and registration for spring term. On the Birmingham campus, it's going to be in the new Academic Success Building. Now, where in the building, I'm not sure. There's supposedly some big room somewhere that they're going to have set up, and I'm sure there'll be signage for it and stuff like this. And what they're going to have, I'll just give you some examples. I may not cover them all. Career Technical, they have a table for that somewhere in this room. They will have 2 tables for general education, okay, somewhere in that room. They'll have 1 for pre-nursing majors somewhere in that room, and they'll have 1 for nursing majors, I think is it. There may be another 1 or 2, but those are the ones I know about. And I believe also in the same room there will be setups for financial aid and other things like this. Now the setup is going to be something like this. At each table there will be an instructor, an administrator, or a staff person at that table, okay, representing each of those areas. There may be more than 1, okay, and they will be, from what I understand, plexiglass in between the student and the staff member, okay, and therefore it's going to be safe. And of course everybody will be masked. Everybody will be masked, so you can't even get into the building unless you've got a mask on. So please bring a mask, and they may have some there available to give you if you don't bring one. but I would say bring a mask, wear a mask onto campus. And so it's going to be as safe as they can make it. They'll keep all the students social distanced and everything else. However, here would be my advice to you. I can't be there because of my health situation, okay? We have the Virtual Advising Center. I just haven't heard a lot of advertising or encouragement or anything else for anyone to use it. And I know that last summer when they first started this new banner program and opened up the Virtual Advisement Center, boy, were we getting things on it all the time. And last summer I was down for, I can't remember if it was 6 or 7 hours a week that I was doing virtual advising in between classes when I wasn't in class. And as a result of that, I was, for the first several weeks, they assigned us blocks of 30-minute blocks, okay? So 6 hours would have 12 blocks. If it was 7 hours, there were 14 blocks, okay? At least to begin with, and even later on, the vast majority of my half-hour intervals were taken, okay? I would get out of class and have a few minutes, and then I'd be right into advising. This fall, I've had 5 hours a week. That's 10 slots I've been available a week, and not a single student has signed up. Now, I don't know what's going on. I don't know if they didn't advertise it well. I don't know what's going on. Now, I've been advising students. They'll call me. They'll email me. Students I've had before, they'll get in touch with me, and I'll do advising when I can. But not a single person has done the virtual advising. And so I don't know. I don't know why. So if I were you, I would get on and sign up for virtual advising. We're still there. We're still out there with hours for virtual advising, and that way you would avoid having to come onto campus. But if you'd rather go to campus and you'd rather have the one-to-one, even though it may be plexiglass in between, advising, do that too. And they can actually help you with the scheduling as well, which you can do somewhat with virtual advising, but I think they may be able to be a little more hands-on with that. So try to get, okay, now I say all that. I know Kara's not coming back in the spring. I don't think Jesus is. Esther, are you going to be back in the spring or not? Your microphone's still off. Esther, you going to be back in the spring or not? Do you know? I see your lights on, but I can't hear you yet. But if this whole class is going to be graduating at the end of this term, which you easily could be, then I'm sort of preaching to the choir here, and it's not making any difference, except for the fact that you know other students, okay? So even if you're not going to be back in the spring, please get the word out. This week, Monday through Thursday, 9 in the morning till 7 in the evening, they will have these advising tables and registration tables set up on both campuses. Birmingham campus, Academic Success Center. I may have forgotten to say this one. On the Bessemer campus, it's going to be in the Ethel Hall Auditorium. Now, that's not the Ethel Hall building on East Campus. We're talking about the Ethel Hall building on the Bessemer campus. And that's the building that's closest to the Civic Center on the Bessemer, closest to the Civic Center on the Bessemer campus. Maybe not closest, but on that end of the campus. And if you go, when you park in the parking lot down below, walk up around the building and come in the main entrance. And when you do that, the auditorium is immediately on your left. If you come in from the parking lot entrance, you have to roam around in the halls down there until you can find the stairwell or an elevator, and then take that up to the main floor, and then wander around the halls there until you can find the Ethel Hall Auditorium. If you come around the back side of the building, which is the main entrance of the building, and you come in the auditorium is right there on your left. Okay, so anyway, it's not a hard building to get around in, but it's just so much easier to come in those doors. Any questions, issues, concerns, problems? I know I talked too long. Sorry about that. All right, let's get to calculus. Okay, we're in Chapter 12, Vector Value Functions. We're in Section 12.2, which is differentiation and integration of vector value functions. We're still on the differentiation part of it right now. We've done example 1 on the top of page 829. We're getting ready to do example 2. Any questions before we hit example 2? Oh, I need one other thing to tell you. I was just noticing how cold my hands are. We've had some furnace problems here at the house. Started, I think, Saturday morning. And we called them this morning, and they said someone would be coming. They said they were going to give me a call half hour before they're going to get here. So it could happen that right in the middle of class, or anytime now in class, the phone could buzz and I need to get with them, and if I'll need to go down and show them where the furnace is and that kind of stuff. So there is a possibility there will be an interruption in class. Hopefully not, but it could happen. And then for two of you who are in differential equations as well, if it hasn't happened by then, it could happen then. So hopefully they'll come by after 4 o'clock when I'm already out of class, but no guarantee of that. I just noticed that when I noticed how cold my hands were, that we got a heat upstairs, but it's not the furnace heat from downstairs. Okay. All right. Any questions? All right. Example 2 on page 829 is a higher order differentiation. Here's a vector value function. R of t is equal to cosine t I plus sine tj plus 2tk. Now, if you haven't noticed already, when I'm in the book, when they're writing a vector, they put it in bold letters. I can't write bold on the screen. So what I do, I put the arrow over it, because vector is a directed line segment. It has direction as well as magnitude. So that's what most vectors I do. But if it happens to be a unit vector, I put the housetop on it. Okay, that is what I consider a symbol for a unit vector. Of course, they just bold in the book. Okay, now we're to find several things with this vector valued function. The first thing they want us to find is r prime of t, the first derivative of this vector value function. What we do, we take the first derivative of each of the component functions. Now these are scalar functions. This is a vector function because it's a vector, and the scalar functions, though, those are the components of that vector function. So how do we take the derivative of a vector value function? Take the derivative of each of the scalar value functions. Okay, so this will be derivative of cosine is minus sine of t, and that will be times I. Derivative of sine is cosine of t, j, and derivative of 2t would be just 2k. Okay. The B part of this problem is asking for the second derivative of r. As a function of t. Well, the derivative of minus sine is minus cosine. because derivative of sine is cosine. Okay, I minus derivative of cosine is minus sine, so minus sine t j, and derivative of 2 is 0. So the second derivative has no z component. It's all within the xy plane. Okay? Now, next thing they're going to ask us to do, I'll put two brackets there, I don't know why. Let's take the dot product of r prime of t and r double prime of t. So that'd be, because these are vectors also, okay, r prime of t dot product with r double prime. Now, of course, a dot product produces a scalar value, so let's see what we get. Oh, here comes Kyle. Okay, I bet you practice went a little long. Okay, let me get Kyle marked here. It's going to take a while. My fingers are getting cold. I don't know why. This morning was pretty fine here, but this afternoon it seems like it's gotten colder inside, and yet I've had the thermostat at the same level up here. Maybe, I don't know. All right, so anyway, Kyle's here. Good to see. Well, not see, but know that you're here. Okay. We're doing example 2 on page 829, section 12.2, differentiation and integration of vector value functions, and chapter 12 is vector value functions. All right, and we had just gotten to the C part here. We have the A part here, r prime, the B part here, r double prime. The C part says take the dot product between those two. What is the dot product between those two? Dot product between any two functions is the product of the components of each of the principal axes, you may say, and add them together. Okay, a dot product produces a scalar answer, not a vector answer. Okay, so this will be minus sine t times minus cosine t is sine t cosine t, positive, because minus times minus is plus. And the dot product here is minus cosine t times sine t, which is also, but that's a minus sine t cosine t. And then the dot product of 2 and 0 is, of course, 0. Well, minus sine t cosine t, plus sine t cosine t minus sine t cosine t, that adds a 0 as well. Now, what does that tell you about r prime and r double prime? Anything? If the dot product is 0, what does that tell you? Anybody? The dot product of two vectors is 0. What does that tell you about those two vectors? They must be orthogonal. In other words, they're at right angles with each other. Okay? So that means in this case, in this function, they're at right angles. Now, we've seen this one before, I'm pretty sure. R of t cosine ti plus sine tj, that's going to be at plus 2tk, that's going to be a helix, okay, which basically is a spring-looking diagram of a circular function. The base, the projection on the xy plane is a circle, and the first derivative of the circle, we're going to get to a little bit later, is tangent to the circle, whereas the second derivative always points toward the center of that circle. So those will be perpendicular to each other. The one pointing tangentially and the one pointing toward the center, if that's a circle rather than an ellipse or something like that, is going to be perpendicular. And then the D part, you probably could almost guess what they're going to ask for there. They're going to ask for the cross product of those two vectors, r prime of t cross r double prime of t. Now, hopefully you remember this as well, because it's been a long week, I'm sure. The cross product of two vectors also produces a vector, okay? And how we calculate that vector is by setting up a determinant. The top row of that determinant is going to be your unit vectors, I, J, K, and then what we're going to do is repeat the first two columns, I and J. Now I'm going to write down that as a determinant, though you really don't take a determinant of a rectangular matrix, only square matrices, but in a 3x3 this is a good technique that works. What's the I component of r prime? You always put the r prime first, or whichever one's listed here first. That goes in right under the unit vectors. That's a minus sine of t. The j component is the cosine of t. The k component is 2. Then we repeat the first two columns again. Minus sine t cosine t. Okay. Then we do the components of the third vector. And that third vector is, of course, minus cosine t minus sine t, 0, because this has a 0 k component, and then repeat the first two columns, minus cosine minus sine. Okay, there's supposed to be a t in there. All right. I hate to do this because my hands are already cold, but I need a little bit of soda. My anemia is still with me. I think I'm getting a little stronger every day, or it could be I'm just getting more used to it, but I really do believe it's getting better a little bit every day, but I'm still so low of energy, so I need to boost a little, and I ate part of my lunch in between my first two classes, so that's probably also robbing some red blood cells, that are trying to digest food now. They're saying, hey, I can't do everything at once. So let's do our cross product. Now, I don't know if you remember this setup, but we do a down diagonal, okay, through the I, the cosine, and the 0, multiplying as we go. Well, that 0 wipes everything out, so that contributes nothing to our cross product. Then we go down the next down diagonal, and this produces a minus cosine, yes, it's so aggravating, minus 2 cosine t j. Okay, go down our third down diagonal, and that gives us a plus, because minus times minus is plus, sine squared t k. All right, now I'm going to, just to try to keep it from being as confusing as possible, I'm going to erase my construction lines here and go my up diagonals. Okay. I think I'm going to take this book out of my lap too. It's way too heavy. All right. Now let's do the up diagonals. Now the difference in the up diagonals, I thought this hadn't changed yet. Okay. The up diagonals are always the negative of what they indicate here. Well, that's a negative times a negative is a positive cosine squared k. So that's a plus cosine squared t k. Okay? The next up diagonal is going to be a plus sine, let's make that 2 sine t I. And the third up diagonal, of course, is a 0 again. Okay? So what do we have? This cross product is going to be 2, and that's not a t there, that was a plus sign. 2 sine t I minus 2 cosine t j. And then what do we have here? Plus sine squared plus cosine squared. Well, what is that? That's just 1. So that's k. For some reason, I did not put my house stop on the j. Okay. So there is the cross product. Cross product is a vector, always. Dot product is always a scalar. This one happened to be 0. Okay. Let's see how the book did on these. R prime of t was minus sine t I plus cosine t j plus 2k. Got it. R double prime was minus cosine t I minus sine t j. Got it. The dot product between the R prime and R double prime was 0. The numeric value 0. That's not the vector 0. Okay. And then the cross product is 2 sine ti minus 2 sine tj plus k, because the k component is sine squared plus cosine squared. All right. Now, I think the next slide shows up on the PowerPoint. So let's go back to PowerPoint. Are there any questions on that before we left it? None so far? Let's see. Oh, here comes Jemanuel. Okay. That gives us 5 students so far. We broke half of the class. My fingers are so cold. This is getting to me. This is so bizarre because this morning it was cooler outside than it is now, but okay. This is 5 students here. Top half of the alphabet 3 out of 4, and bottom half of the alphabet 2 out of 4. So if y'all can get one more in here, y'all will be even. Okay, not that y'all are competing or anything, are you? Okay. I'm getting my wires all tangled here. Okay, so let's go back to, and by the way, Jemanuel, we're in Chapter 12, Vector Value Functions, Section 12.2, Differentiation and Integration of Vector Value Functions, and we're on the top of page 830, just before we get to example 3. So I was just going to go there. Now that was the last slide of example 1, which we did last Monday. Okay, I think. No, it isn't. This is the top of page 830. Evidently, when I clicked in, it advanced the slide. Okay, the parameterization, and I can't say that word the way it's supposed to. parameterization. I always want to put an E in between the T and the R. Parameterization is parameterization of the curve represented by the vector value function R of t is equal to f of ti plus g of tj plus h of tk. That parameterization of that curve represented by that function is smooth on an open interval I when the first derivative of f, the first derivative of g, and the first derivative of h are continuous on I. So that's a smooth function on that open interval I when that is true. And r prime of 0 is not equal, r prime of t is not equal to 0 for any value of t in that interval. Okay. Now, it's smooth on the interval when the first derivatives are continuous, and also that the r prime of t is not 0 for any value t on that interval. Not exactly clear, intuitively in my mind anyway, of why that's true. Usually a first derivative equals 0 just has it, 0. Why is that a requirement here? Okay, I'm not sure we're going to answer the question. Let's move on to example 3 and see what it shows us. Find the intervals on which the epicycloid C given by r of t is equal to 5 cosine minus cosine 5t I plus 5 sine minus 5 minus sine 5t j is where t is anywhere from 0 to 2 pi, where that's smooth. Okay, find the intervals of that, when it's smooth. Well, what is required for smoothness? That the first derivatives of each of the function be continuous on I, and that the first derivative is not equal to 0. Now, okay, let me take this back. The first derivative of the entire function, not the individual component functions, but the entire function is not 0 for any value t on that interval. Okay, so let's take our derivatives. Okay, if I could get my pen to show up. It's in my hand backward. No wonder it wasn't showing up. Here we go. R, I can't draw bold, so I put an arrow over it. R prime of t, what would it be in, excuse me, I'm so sorry. So sick and tired of being sick and tired, but I guess it just comes with the territory. Okay, what would be the first derivative of this first part of that function? Oops. Its derivative of sine is, of cosine is minus sine. So the 5 was just the coefficient there, it's there. Okay, derivative of cosine, again, is minus 5, but then you have a chain rule here, so that's going to be another minus 5 sine t, and that's going to be your I component. Okay, plus derivative of sine is cosine, so that's going to be 5 cosine t minus, okay, derivative, sorry, goodness, my hands are cold. Derivative of minus sine of 5t would be minus 5 times the cosine of 5t. Okay, and that'll be the j component, and that'll be good from 0 less than or equal to t less than or equal to 2 pi. Okay. Find the intervals on which that epicycloid is smooth between 0 and 2 pi. Okay, what were the requirements? That the derivative of the first thing cannot be 0. No, it has to be, oops, went the wrong way. Has to be continuous. Each of these derivatives of these component functions have to be continuous, and that the whole function r prime of t not equals 0 for any value t on the interval. Okay, so that's what we've got here. Well, let's clean this up just a little bit. This will be minus 10 sine t I, and this is plus 0 j. Okay, and we don't even have a k because k wasn't there to begin with. Okay, now certainly this is a continuous function everywhere, t 0 to 2 pi. This is a continuous function everywhere, 0 to 2 pi. Okay, however, the r prime of t cannot be 0 for any value t. Well, where would that be? Sine of t is 0 when t is equal to 0, which is included here. Where is my pen? There it is. Okay, that's included. Okay, 2 pi would be 0, but also pi. So the intervals on which the epicycloid is smooth would be the interval not counting 0, but 0 to pi. Okay. I've got to get some more caffeine, sorry. It doesn't seem to be very effective today. So, on the interval 0 to pi, but not counting pi, it's smooth there. But then again, starting at pi but not counting pi, up to 2 pi but not counting 2 pi, is smooth again. Because any place where the sine is 0 would produce a 0 first derivative, and if that was the case, not smooth, not guaranteed to be smooth there. So these are the two intervals between 0 and 2 pi where your the epicycloid would be smooth. Okay, I blew something here. Okay, this is supposed to be a 5t there. 5 minus 5 sine t minus 5 times cosine of 5t. I got that in here. I mean sine of 5t. I've got it in here, but I forgot to write it there. Okay, and that messes up everything. So I'm sorry. I was just looking at this saying this doesn't seem right. Okay, and it isn't right because of that. This does not add. Okay, it's nothing nearly as simple as what I said. Okay, what you can do is factor out of 5 minus 5 times sine t minus sine of 5t plus 5 times the cosine t minus cosine 5t j. Okay, everywhere between 0 and 2 pi. All right, this is a completely different issue. Okay, number 1, sine t minus 5 sine t, continuous everywhere. 5 minus 5 times that, continuous everywhere. 5 times cosine t minus cosine 5t, continuous everywhere. Sines and cosines are continuous everywhere. No places where they aren't. So that's not an issue. Remember, that was the first thing here. Anywhere where your first derivatives, why did that do that? Okay. Did you quit? This is just, I guess what I did was lay my pad on there and it was just driving everything crazy. Okay, here we are. Okay. Okay. So the first of these is where all these first derivatives are continuous. These first derivatives are continuous everywhere. That's continuous everywhere. This is continuous everywhere. Okay? Second issue, though, is that the entire function, first derivative function, cannot be 0. Now that really should be a 0 vector there. Okay? I didn't notice that the first time. That should be bolded to be the 0 vector, because that's a vector, this has to be a vector. Okay? Did they get it right in the book? Goodness, my hands are so cold. Yeah, in the book they had it as a 0 vector on the slide set. Whoever did the graphics for the course didn't quite get that one. Okay. For any value t in the interval. So basically what we're looking for are places where, if I could get my pen to show up, here we go, minus 5 times sine t minus 5 sine t, sine of 5t, is equal to 0, and that's also equal to 5 times cosine t minus cosine 5t. Yeah, that also is 0. So it's the place where both of those have to be 0 at the same time. Okay? So let's find the places where this one is 0. Well, the minus 5 is not going to matter any. You can divide that away. So this is saying, I'm sorry, where sine and this, y'all let me get away with this? That's a plus. If I factor out the minus 5, that's a plus in there. Sine of t, and I factored out the 5 too. I don't know why that's still in there. Y'all let me get away with that too, didn't you? Sine of t is equal to minus sine of 5t. Everywhere that's true, that would be 0. Okay? Well, where in the world is that true? Okay? Trying to think the best way to do this. I don't believe it's by doing multiple angle formulas. That would get really, really, really messy. Let's see which way the book runs on this one. They just tell you what they are, and that's it. Sorry. They don't tell you how they got them. They just say where they got them. Okay? Now, and I guess they just do it by observation. Well, first place, I guess I got a sign wrong, didn't I? Well, it would help, perhaps, if I copied the... No, I think I got something wrong. I think I did it right. In the book, they have minus 5 sine t plus 5 sine 5t. And that's not right, because the derivative of... Yes, it is. Okay, that is a plus. Sorry about that, folks. And that made this a minus. Well, doesn't matter. So we're back to this again. Sorry, y'all get me. And then this one, this one is wrong too. No, that one's... Goodness, I can't believe this. Derivative... Okay, let me start over. Derivative of cosine minus sine. Derivative of that is minus. That makes that. Derivative of this is sine. Yeah, so both of these are correct now. Okay. 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 Now, so this is where sine t is equal to 5 is equal to sine of 5t. If I can ever get my words to come out right. Okay. Now let's think about that for a minute. Sine t would start like this. Okay. Starts at 0, and at pi halves it's at 1. At pi it would be at 0 again. At 3 halves pi it would be back at, it would be down negative 1. At 2 pi it would be back at 0. So there's your basic sine function. Alright, now where the sine of 5t would be, and that's what we're dealing with here, what you're doing there, that is a horizontal shrink. Okay, almost said it backwards. Horizontal shrink. That would be everywhere that 5t is equal to n pi. That would be where your zeros are. So that would be t is equal to pi fifths n. Okay, where n is any integer. Well, we're only going to go from 0 to 2 pi. Okay, so we're only going that far. Okay, so what that would mean is that you would be compress this by a factor of 5. Okay, so this would be pi tenths. Let's see, is that right? Goodness, this is hard to do graphically because it's so complex here. Basically what they say and drawing the figure is actually the best way to do it. I can't believe I'm saying that, because usually that's not what I like to do. But if you do draw the figure, you see that the places where your first derivative is 0 are at your half pi's. Okay. And excuse me, I've got to sneeze. Excuse me. Sorry. Okay. Because they've got to both be 0 at the same time. Okay. And in other words, this expression is equal, if I could get my pen to show up. Yuck, where is it? There it is. Okay. That this is equal to that. Okay. And I think remember, that's the minus sign, because I factored out that. Okay. Now, and there's no really easy way to do that algebraically that I can see. They just show you, here's the graph, there are the places where it's not smooth. I'm sure there's a better way to do it than that, but that's what they're basically are saying. And I believe it would come down to where each of those would cancel each other out. Don't know that's going to be the absolute case, but it seems like that's what it would be. Where is sine t equal to cosine t, and whereas that would be the same places where sine of 5t was equal to cosine 5t. And I don't know. They just refer you to the figure. They do not tell you or show you how they got that rendition there. And when you do it, you'll see that's entirely the case. So I'm going to just scroll down and we'll see. Let me erase my ink here. Sorry, I thought this would be a relative easy one to do. But the derivative of this is exactly what we got, minus 5 sine t plus 5 sine 5t, sine of 5t, I, plus 5 cosine t minus 5 cosine 5t, j. Okay? Now, it says in the interval from 0 to 2 pi, the only values of t for which r prime is equal to, that this is a 0 and that's a 0 at the same ones. And here they just they just give them to you. They don't tell you how they get them. But let's take a look and see. When t is equal to 0, of course, sine of t is 0 and sine of 5t is 0. So that first component is 0. We know that. Okay? Here, though, sine of 5 times cosine of t, cosine of 0, is 1, so that would be 5. And then this one, when t is equal to 0, this is also cosine of 5t is 1, and 1, I'm sorry. So 5 times cosine t, that would be 5, minus 5, that would be 1. That would be 0. So certainly those two are both zeros at 0. Now, how do we know about the pi halves? Sine of pi halves is 1. This will be a minus 5. Sine of 5 halves pi, that's what you get if you plug in a pi halves here. Well, sine of 5 has pi, sine of 1/2 pi is 1, 3 has pi is -1, and 5 has pi is 1 again. So sure enough, that goes to 0 again. -5 plus 5 is 0. This one does the same thing. Oh, well, I'm sorry. Yeah, except now there are zeros to begin with. Cosine of pi halves is 0, and cosine of 5 halves pi is 0, because cosine is 0 at all your half pi's. So that will certainly work. Now, we haven't proven there's none in between this, but we have verified that these are true. So everywhere that, and this is what I was saying before, that sine of t and sine of 5t have the same values, okay, then the sum of those has to be, or let's see, yeah, has the same value, then because one's plus and one minus, they've got to be equal. So that happens at the half pi's and at the pi's, okay, both for sines and for cosines, and they happen at the same time. So therefore, these are the places where your r prime is 0. The entire function is 0. The first derivative is 0. At 0, pi halves pi, 3 halves pi, and 2 pi, because 2 pi was included in this interval. Okay, now the slope there, the first derivatives there, it's pretty obvious to me that this derivative is 0 there and this one is 0 there. It's not quite so obvious to me. Well, okay, now remember, it's not where they're both 0, but where they're equal. And this is a near vertical slope here, and that's a near vertical slope. This is positive, that's negative, but at that point, they're both exactly vertical. So, and here, the first derivative would be 0 at both, and there it would be. Okay. Smooth in between those intervals. Okay. But at that juncture, at those cusps, it's not smooth. It's definitely not smooth. Okay. Now, let's move on. That was enough. In figure 1210, that's this one right here, okay, note that the curve is not smooth at the points where the curve makes abrupt changes in directions. Such of those points are called, I called them cusps. The book also calls them nodes, okay. Same type thing. They seem to like nodes better. Those are definitely cusps in my mind. So here's some of the properties of your derivative. And I'm sorry, I'm just really cold. Okay, if r and u are differentiable vector value functions of t, the independent variable, and w is a differentiable real valued function of t, okay, so r and u are differentiable vector value functions of t, and w is a differentiable real valued function of t, and let c be any old scalar. Okay, now the first of these, d by dt, that's your independent variable, t, of a scalar times a vector function, pull the scalar on the outside, and that's a c times the derivative of the vector value function. Okay, that's your scalar product rule. Your sum and difference, derivatives of sum and difference, would be exactly, I hope, as you would expect. It would be r prime of t plus or minus u prime of t. And that's exactly what you get here. That's your vector addition. The derivative of vector addition will be the Derivative of a sum or difference of two vectors is the sum or difference of their derivatives. Okay, the next one. Now this is where you get your scalars and your vectors kind of mixed up here. Derivative of a product of your scalar function and a let's call it a real valued function and a vector valued function. That would be the first times the derivative of the vector value function plus the derivative of the scalar value function times the vector value function. Now notice here that's sort of a chain rule, a product rule type application here, but in doing the product rule, it's a scalar function times a vector function. Derivative of that is a scalar function times a vector function plus a scalar function times a vector function. So it comes out being a vector function, which I think we would probably suspect it would. Okay. Now this time the product is not going to be between a scalar and a vector, but between a vector and a vector. Well, there's two types of those. One is a dot product, one's a cross product. So let's see what that will be for the dot product. d by dt of r dot u would be r times the derivative of u plus r prime times the derivative times u. Derivative of r times u. Same type deal here. Keep the dot products in their place. Remember, this now becomes, though, a scalar answer. So the derivative with respect to t of a scalar is going to be a scalar. Well, this is a scalar and that's a scalar. So your answer will be a scalar, and it'll be precisely the same rule that we usually use for the product rule. Okay? Now, the cross product rule. This is the dot product rule. This is the cross product rule. d by dt of r cross u is r cross u prime plus r prime cross u. Okay. Here you have to be careful. Up here it really doesn't matter. You could do r prime dot u plus r dot u prime. It doesn't matter. That's a scalar, that's a scalar. You're just adding two scalars together. Here it does matter. You have to have the first times the derivative of the second plus the second times the derivative plus the derivative of the first cross the second. Okay. Why am I saying that? Because if you reverse the order of either one of those crosses, you're going to get a negative of what you would get otherwise. So this one you have to pay attention to the order. R cross u plus r cross u prime plus r prime cross u. Has to be that way. Okay. Now this is one, d by dt of a composite, a vector function composed with a scalar function. And this is just like your, excuse me, I'm so sorry. Just like your chain rule is r prime at w of t times w prime of t. Just like your chain rule. And you continue that. If it's a composite of a vector function composed with a scalar function. Okay. And number 7, last one. If r of t dotted with itself is a constant, if that's a constant, not a function of t, you know it's a scalar, of course. R dot r is a scalar. But if that scalar has no t dependence in it, that's just some constant, then r dot r prime has to be 0. Now, That may not be intuitively obvious why that's true, but if you remember when we were talking about dot products, R dot R basically, if my memory's right, is the square root of is the magnitude of R squared, okay, which is a constant, okay. Now, but not a function of time, okay, so that's just or of t, whatever your t is. So that means that then they must be perpendicular. Oh well, if the dot product is a constant with no t dependence, then that's the maximum dot product you will have, meaning the vectors are parallel to, well, of course they're the same vector. Then the r dot r prime has got to be 0, because those then have to be perpendicular to each other. Okay, that's sort of a awkward rendition of that, but that's what you got. Now, they talk about proving properties 4 and 5 here. I'll let you read those to your heart's content, because we really need to move on. Here's example 4. Okay. I'm sorry, all this chilling, stuffing up pretty badly. Here's R of t right there. R of t is 1 over 2I minus j plus log tk. Here's U of t, t squared I minus 2tj plus k. Find each derivative. Well, the first of these is the derivative of the dot product of those two. Now, remember, you have a couple of ways of doing this. You could literally take the dot product of R of t and U of t, and then that's going to give you a scalar function, and then take the derivative of that. We'll do that, but let's first do it the way they suggest, by the theorem we just had. This would be R of t times dotted with U prime of t, if I could get the dots to show up, U prime of t, if I could get the t's to show up, plus R prime of t dotted with U of t. Now, this actually seems like to me this is a harder way to do it, okay, because you've got to take first your derivatives here, okay, and that would be minus 1 over t squared, okay, I plus 0j, okay, plus 1 over t k. That would be your R prime of t. Okay, your U prime of t, which you're going to need here, this is going to be 2ti minus t minus 2, sorry, t for 2, and that's going to have a 0. Oh, yuck. Okay, that's j, okay, and 0k. So if you took those and dotted them, R with U prime, that's this one dotted with that one, get out of there. Dot product of those two, okay, that would be 2t times 1 over t, that would be just 2, Okay, that's the I terms. The J terms would be, let's see, -1 times 0. Okay, that would be a 0. And then your K terms, contribution from that, would be log T times 0. And that would be, so this just would be 2. Okay, plus, now let's do this part, R prime, which is this one, times dotted with U. That's -1 over t squared times 1 over t squared. That's going to be a -1. That's the I contribution. Your J contribution would be a 0 times that. That would be a 0. And your K contribution would be 1 over t times 1. That would be -1 over t. Okay? And when you add those together, you get 1 minus 1 over t. And again, this is a scalar function. Now, let's see if doing it the other way. Let's dot product first. Okay, and this would be d by dt is equal to 1 over t times t squared would just be t. -1 times a minus 2t would be plus 2t, and log t times 1 is plus log t. Okay, so this would be, now it seems like I got a sign wrong here, but I don't see where it is. Maybe it was in my first rendition. I'm going to have to go back and check that. Okay, if you take the derivative of this scalar function now, this would be 3t, so that would be derivative of that would be 3 plus 1 over t. And that's not the same. So I have done something stupidly wrong here. Seems like this all day this way. -1 over t squared, that's right, I'm pretty sure. T to the -1, derivative of that be -1 times t to the -2, that's right. And derivative of this is 0, and derivative of this is 1 over t. Derivative of this is 2t, derivative of this is -2, and derivative of that is 0. Okay, now let's go back and do this. R times u prime dotted with u prime, that would be this times that, that's 2, exactly what I got there, plus this times that would be, oh, there's where I messed up. This would be a 2, these two dotted, and then when you dot these two, you get another plus 2. So that would give you 4. Okay, and when you dot that, you get a 0. Okay, and then when you do, I'm going to have to erase some of my lines here. Where is my pen? There we go. This is so aggravating. Goodness gracious, this keeps screwing up. Okay, let's see if I can get this to do it. Okay, let me erase some of these so we can see them better. Okay, so that gave you a 4 there. All right, now let's do this one dotted with u, r prime times u, the second one here. That would be a minus 1. That's correct. Okay. And that would give you a 0, and this gives you a plus 1 over t. Okay, so now we got it right. 4 minus 1 is 3 plus 1 over t. And as I said from the beginning, I think the easier way would be to do the dot product first and then take the derivative. And that sure seemed to be the case here, because otherwise you're taking two derivatives, each of them vector derivatives, and then you're doing two dot products. Whereas this one, you do one dot product and one derivative. So it's so much easier doing it that way. Okay, but we did verify. Now, second says, let's do u dot u prime. Okay, we got u here and we got u prime here. There's u prime. Excuse me. And we're going to do a cross product of these. Now, how about this one? I have a feeling still it's going to be far better to do the cross product first. So let's do that. That's going to be I, J, K, I, J. Okay? And the u is going to be a t squared minus 2t 1 t squared minus 2t. And your u prime is going to be a 2t minus 2. Wait, you let me get away with that. Yuck. I don't know where the brain is today. This is a minus 2t. Okay, not minus 2t squared. Okay, from right there. Okay, this is going to be a minus 2, and this is going to be a 0. And then repeat the first two, 2t minus 2. Okay, take sort of a determinant of that. That will give you a 0. This gives you a 2tj, 2tj, and your third down diagonal would be a minus 2t squared k. Okay, I'm going to erase those construction lines because they will tend to get messy and in the way. And now let's do our up diagonals. That's a positive 4t squared k. Okay, next up diagonal gives you a positive 2i, and your last one is just going to be a 0. So what does that give you? 2i plus 2tj plus 2t squared k. Now, take a derivative of that vector function and you get, if I could get my pen to show up, there it is, 2j plus 4tk. Now, to me, that's the easy way to do that one. Okay, let's see what it would have been like if we had done our the way the theory told us in the last slide. That would have been u double prime, so you have to take another derivative of that. U cross u double prime plus u prime cross u prime. Now, that part's actually easier. u prime cross u prime is 0, because a vector crossed with itself is always 0. A vector dotted with itself is not. And here comes James. Good deal. Okay, let me get him in here. And there we go. So now the top half of the alphabet is 3 out of 4. The bottom half of the alphabet is 3 out of 4. So evened it up. 6 people here. Good to see. Now, James, we're doing example 4 in chapter 12, vector value functions, section 12.2, differentiation and integration of vector value functions. And we just finished talking about a theorem 12.2, which gave you properties of derivatives, which gave you some of the product formulas as well as just derivatives, okay? And that's what we're using in example 4, and we're doing the B part now. And we came up with one answer, what I consider the easy way of doing it, but I wanted to show you the other way of looking at it, okay? So what I'm going to do is, if I can get I can't get my window to open here. And goodness gracious, let's see what, here we go. I'm going to erase most of what we've got on the slide. Not everything, but a lot of it. Okay, we don't need our primes anymore. We're doing the B part now. We don't need R prime. I can't talk. We will need this one. Okay. All right. And I don't think we need this anymore because those are dot products here. I can't get this to erase. Don't think we need that anymore. Okay. And then I'm hoping we don't need this anymore either. If I made a mistake there, that's just too bad. Okay. I should have checked that to make sure that was the answer before I started erasing. Let me do that quickly. 2J plus 4TK. Yeah, I thought that was right. Okay. I just wanted to leave the answer we got the other way. Okay. And I have just been all over the place in bad answers today. Okay. Now this one we're going to need a U double prime. And that's just going to be 2I. Right? That will go to 0 then. Now, what we just had learned in our theorem, that this would be, and bear with me on my notation, U cross U double prime plus U prime cross U prime. That's basically what we learned from our theorem. Now, this is easier to do by the theorem, whereas the last one wasn't bad. But look at this. This we know goes to 0 because a vector crossed with itself is 0. Okay, that's just one of the properties of cross products. So this then becomes the I, J, if I could write, K, I, J. I'm slanting too much here, I don't know why. U cross U double prime. Well, U would be your T squared minus 2T 1. And then repeat these. T squared minus 2T. Okay. and then this one would just be 2, 0, 0, 2, 0. That's going to be a far easier one to do, I think, because your first down diagonal, if I can find my pen here, that's a 0, and this gives us 2j, if I could write, and this gives us another 0. Okay, so let's wipe out my construction lines there just to make it easier to read. Okay, and then the up diagonals will be plus 4t k, and that gives us a 0, and that gives us a 0. So there's the answer this way. Okay, and they are exactly the same. Okay, this one was easier to do. Okay, so sometimes it's easier to do the vector multiplication, then take the derivative. Other times it's better to do the product rule of the derivative of the vector multiplication. We saw in the first one there, far easier to do, take the dot product first and then take the derivative of that. I think that's almost always going to be the case for the dot product. With the cross product though, I don't know if you can say always, but this one I think, especially if it's something like this, u cross u prime, you know the part of that is going to be u prime cross u prime, and that's going to be 0. So I think that may wind up in many circumstances being easier. Okay, now let's move on to, let's see how they do it, just to see what they do. Let's erase all the ink. Whoa, okay. Okay. Now what they're going to do first is, because r prime is that minus 1 over t squared plus 1 over t, minus 1 over t squared I plus 1 over tj, and u prime, I don't know why they put them in, I guess I do, in different sizes and stuff, but anyway, u prime is 2t I minus 2j. You have the derivative of the dot product equaling, this is using the product rule for a dot product, r dot u prime plus r prime dot u. Now, this to me is not the easy way to do it, but we did it this way too, just because I thought that's what they wanted you to do, and they did. So that first r was 1 over ti minus j plus log tk, dot this u prime, which is 2ti minus 2j, plus r prime, that's this one, minus 1 over ti plus 1 over t squared I plus 1 over tk, dotted with the original u, which was t squared I minus 2tj plus k. Okay, when you dot these two together, this gives you a 2. Dot these two together, you get another 2, so 2 plus 2 is 4, high level math today. Dot this with nothing and you get 0, so the 4 comes from here, and then when you dot these two together, you get a minus 1. Okay, dot these two together, you get a minus 2. So, no, I'm sorry, this doesn't have a j component, so that's a 0, and this gives you 1 over t as that product. So that gives you a 4 plus 4 minus 1 plus, well, here it is. 2 plus 2 is 4 minus 1, that would be a 3 plus 1 over t. Okay, that's this dotted with 1. Okay, and that gives you 3 plus 1 over t. Now, they repeat their u prime here and also do their u double prime here. And then when you do this derivative of a cross product, that's u cross u double prime, that's this, the first times the derivative of the second, okay, plus the derivative of the first times the second, okay. Whoa. Okay. Well, they do their thing here, and they note right off the top, this is going to give you a 0. So this is going to give you the u, which they don't show here, was t squared minus 2t plus 1, and 200 is the last part. And when you do that, all you do is this times derivative here, okay, determinant here, okay, so it'd be 2 times j minus or plus 2t, so that would be 2j plus 2tk. Oh my goodness, did they ever go into the gory detail. This, of course, gives you a 0, and I sure wouldn't have done it this way, but you know, you get the same answer, 2j plus 4tk. Wow. Okay. But they don't assume you've had determinants before, but if you have, you know that's the easy way to do it. Okay. Now we're on page 832, and how are we doing on time? We got 5 minutes. Let's see how far we can get there. Integration of vector value functions, I hope you would guess, would be the following definition is a consequence of the definition of the derivative of a vector value function. Okay, but now we're talking about integration. The definition of integration of vector value functions, if r of t is f of ti plus g of tj, where f and g are continuous on some interval a to b, then the integration of that r of t would be the integration of the I component plus the integration of the j component. Okay, and this is just simply a scalar valued function that you're integrating. That's the scalar value function that you're integrating, and it's definite, and that's an indefinite integral. The definite integral on that interval from a to b, where a is less than or equal to t is less than or equal to b, which is exactly what that means, okay, that definite integral would just be the definite integral of your f of t, integral of f of t dt, I plus the integral of g of t dt j. Okay, now that's in 2 dimensions and 3 dimensions, same deal. If f, g, and h are continuous on the interval a to b, indefinite integral is this. Now I've got one little problem with this, but it's not a major problem, but just a little one, and this would be integral of f of t dt I plus interval of g of t dt j. You just take the integral of each of the scalar functions, okay? Definite integral would then be just that, the definite integral of the scalar function here, here, and here. Now what you don't see either here or any plus c's, but you know they've got to be there. This will give you a plus c, that will give you a plus c. This will give you a plus c, that'll give you a plus c, and that'll give you a plus c. And what you have then is a, say, a c1i plus a c2j. That's just some scalar vector. I mean, I'm sorry, that's a dumb way to say it. Constant vector. Constant vector. And here you get a constant vector here too. So what you don't see here is these always come up with constant vectors added to it. This, of course, the definite integrals do not, because you you're evaluating those. The antiderivative of a vector value function is a family of vector value functions, all differing by some constant vector c. That's what I was telling you about, that constant vector c. Now they choose to make it a capital. I don't know why, okay, but they do. For instance, if r of t is a three-dimensional vector value function, then the indefinite integral, the integral of r of t dt, you obtain three constants of integration. One for your I component, one for your j component, and one for the k component. Okay, now you've got these as your variable. Okay, I'm sorry, the phone's ringing downstairs. We're a minute away. We're going to have to end the class here because that may be the people. So sorry about cutting you short today. We'll pick up with this slide. Well, I think the phone quit ringing, so we'll finish this. Okay, your f prime here is that. G prime here is your integrand, just like it always was. H prime here is that. These are the antiderivatives of that, and these are your constants. But remember, this expression right here was followed by an I. This expression was followed by a J. This expression was followed by a K. So there's your vector value function, f of ti plus g of tk plus h of tk, but also then your ci, c1i plus c2j plus c3k, that's your constant vector added at the end. Okay, those three scalar constants produce one vector constant of integration. That was an easier way of saying that this gives you a constant I component, a constant j component, and a constant k component. These three give you your variable components of I, j, and k. So that gives you your r of t, which is your antiderivative of this, and this then gives you your constant vector, capital C. Okay? And again, if you took the derivative of this, you should get what's in here. Okay, and the constant wouldn't contribute anything because derivative of a constant is 0. All right, that gets us up to example 5, so that's a better probably place to stop. We did run over a minute, sorry about that. We'll pick up with example 5 next time. Let's see how many homework exercises. Oh, we came so close to finishing. Do any of the odds 3 through 9, they are all at Calc Chat, 5's at Calc View. Do any of the odds 11 through 17, they're all at Calc Chat. Do 19 or 21, they're both at Calc Chat. Do any of the odds 23 to 20, either 23 or 25, they're both at Calc Chat. 23's at Calc View. And then any of the odds 27 to 33, they're all at Calc Chat. 27's at Calc View. Do 35, it's a Calc Chat and Calc View. Do 37, it's a Calc Chat only. Okay, then do any of the odds 39 to 45, they're all at Calc Chat. 41's at Calc View, and we'll pick up from there next time. Any questions? Okay, for some reason I have an extra thing here, but that I don't think is important. Okay. All right. If there's no questions, I'm going to stop the sharing. And anything before we leave? Okay. So I'll end the meeting for all of us. Have a good couple of days. Those who are coming back, try to get registered. I'd say preferably by your virtual advising center and register yourself. But if you really want to go to campus, you can go to campus any day this week, 9 to either campus, Birmingham or Bessemer, 9 to 7, 9 in the morning till 7 in the evening. And on the Birmingham campus, it's in the new Academic Success Center. On the Bessemer campus, it's in the Ethel Hall Auditorium. That's not the Ethel Hall building. On the East campus, that's the Ethel Hall building on the Bessemer campus, which is fairly close to the Bessemer Civic Center. Not super close, but it's the building sort of closest to that. All right, good deal, folks. Any questions before I close out? We'll see you on Wednesday. Well, some of you will see tomorrow, okay? Well, a few of you I'll see in half an hour, okay? Bye-bye.